Hello everybody and welcome to Nuclear Physics Lesson 3. Now in the last lesson we focused on NZ graphs, and just to remind you, N on the vertical axis was the number of neutrons and Z on the horizontal axis was the number of protons. So we looked at NZ graphs and we looked at some of the different regions on the NZ graphs and nuclei in different regions, what mode of radioactive decay they were more likely to undergo. In today's lesson, we're going to be focusing more on some fact-based knowledge, so a little bit different, probably a little bit shorter than usual lessons, but definitely facts that we need to know, understand, and obviously when it comes to exams, we need to be able to bring these facts and recall these facts, hopefully with ease. Firstly, for this lesson then, we're going to look at gamma decay. We're going to spend a little bit of time reminding ourselves what we would have done in year 1 to do with gamma decay and some of the equations that are associated with gamma particles. And then we're going to look at how that relates specifically to radioactivity and nuclei that emit gamma radiation. So firstly, a gamma particle we know is a photon, and gamma is part of the electromagnetic spectrum. Now, because it is part of the electromagnetic spectrum, a photon has no mass. The equations that we would have learned last year, we would have had E is equal to hf, or that would be equal to hc over lambda, where h is Planck's constant, c is the speed of light, f is the frequency, and lambda is the wavelength of that photon. Just to remind you of some typical values then, for a photon, a typical energy value would be of the order of mega electron volts. Now, mega electron volts tend to be of the order of 10 to the minus 13 of a joule. If you remember back of how to convert from joules into electron volts, 1 electron volt is 1.6 times 10 to the minus 19 joules. So a mega electron volt, we multiply both sides by 10 to the 6 or a million, and therefore we get of the order of 10 to the minus 13 joules. For energies of the order of 10 to the minus 13 joules, if we sort of roughly plug some numbers in through the equation E equals hc over lambda, what we end up with is that the wavelengths for most of these photons are going to be of the order of around about 10 to the minus 12 of a metre. Now obviously that 10 to the minus 12 of a metre will be at the lower end of the wavelength spectrum when it comes to the electromagnetic spectrum. Energy 10 to the minus 13 of a joule, that is actually at the high energy end. You've got to remember that the numbers that we're dealing with when we're talking about the electromagnetic spectrum are actually quite small. So 10 to the minus 13 of a joule does really end up at that higher end of the energy that we're going to be expecting in the electromagnetic spectrum, or more specifically from a photon. Now, moving our knowledge on to a more year 2 A-level level. What I want you to do is imagine that we have some kind of radioactive source, and that radioactive source emits mainly gamma radiation. Now of course, if it did emit alpha and beta radiation, we could very easily, from an experimental point of view, put some aluminium around the source in order to absorb the alpha and the beta, and therefore we would just be left with the gamma. But for the purposes of what we're looking at right now, I just want you to ignore the alpha and beta emission and just focus on the gamma itself. The next stage in our thinking is to imagine that we have a detector that can detect our radiation. Excuse my poor drawing here. And the detector that we tend to use is called a GM tube. Now, we're not going to look too much at how a GM tube works right now, but that's something that we can focus on in forthcoming lessons. Now, the GM tube would normally be hooked up to some kind of computer or some kind of counter that will count the number of radioactive particles that it detects. What we're interested in is the intensity of the gamma radiation. Now, intensity is an interesting measure. Intensity is defined as the energy per unit time per unit area. So as a rough idea, intensity is equal to energy divided by area. That will obviously give you an idea of the number of particles per second that a GM tube or some kind of radiation detector would be counting. Now, what we're really interested in today is this idea that intensity is inversely proportional to some kind of area. The reason why we say it's proportional or inversely proportional to an area is that as our source emits radiation, it will spread out in the form of a sphere. So obviously it will spread out in 3 dimensions. Any point on a sphere, obviously with a constant radius, should, as long as everything has been emitted uniformly, should be able to detect, or a GM tube at that point should be able to detect the same number of radioactive particles passing through that point in a given time. As we move the detector, the GM tube, further away, so we increase the distance r from the source, that sphere gets bigger and bigger and bigger. Because you're emitting roughly the same amount of gamma radiation from the source every second, it's spreading out and becoming fewer and further between for a small point on the surface of that sphere. Because we're talking about the surface of the sphere, the area that we are referring to in this equation or in this relationship is all to do with the surface area of a sphere. Now, from geometry, the surface area of a sphere is 4 pi r squared. When we look at a proportionality relationship, then we tend to ignore any constants that are associated in the relationship. And obviously here we know that both 4 and pi are just numbers, they are constants. And therefore what we're left with is that the intensity of a gamma source, and I probably shouldn't really put an equal sign there, so let's just get rid of the equal sign, I should be using a proportional sign, that the intensity is proportional to 1 over the distance squared. Now obviously we know it's proportional to 1 over the area, and we know that the area that we're interested in is 4 pi r squared that we've written. But as I said, when we deal with proportionality relationships, we ignore the constants, and what we're left with is that intensity is proportional to 1 over the distance squared. What we have here then is what's known as an inverse square law. And if you've already been following the electric fields topic, we will have already seen an inverse square law when we introduced the idea of Coulomb's law. In Coulomb's law, we had that the force was proportional to 1 over the distance squared. Here, when we're talking about gamma decay, the intensity of detected gamma radiation is inversely proportional to the distance squared, the distance being the distance between the source and the detector. The idea then behind how an inverse square law works is exactly the same. Just like we said before, if you were to double the distance, you would have a quarter of the intensity of gamma radiation. If you were to triple the distance, you would have a ninth, quadruple the distance, a 16th of the intensity, and so on. What we'll move on to now is the more fact-based knowledge that you need. These kind of questions may well come up in an exam as a 6-mark question, so we'll just go through some of the details of what you need to know. Firstly, we'll look at background radiation. Now, radiation and radioactive particles are moving through the atmosphere and moving through buildings and moving through us all the time. The doses, though, from background radiation are extremely low, and they're at a level that's low enough that isn't going to cause any lasting damage to our bodies, even over the space of our lifetime. Fortunately, where we are, and especially where we are in the UK, the risk is extremely low, and like I said, it's not going to cause us any health issues in the long term. Now you can see from the pie chart that around about half of all of the background radiation that we will experience comes from radon gas in the ground. On the screen then is a UK map that shows where the risk areas for radon gas are. The darker brown areas show you where there's a higher risk or a higher concentration of radon gas coming from the ground, and in the white areas that's where there is less of a concentration. Now fortunately in the West Midlands we are somewhere around the red dot there, so you can see we are in a low concentration area. There's a streak of radon gas, or a sort of corridor of radon gas just to the south of us, which starts around about Bristol and comes up in between sort of Leicester and Peterborough, which are around about there, and comes up to about Nottingham, which is at the top there. But like I said, fortunately that is to the south and to the east of us, so we're not really affected by that bit. You can see that over in Wales the concentrations are slightly higher, and obviously down in the southwest in Devon, South Devon and into Cornwall, there are obviously quite high concentrations there. Now if you were really sad enough, you could go to the website ukradon.org, and in that website you are able to put your postcode in there and find out, at least for a small area around where you live, what the risk from radon is. The risk in my area where I live is less than 1%, so that's obviously very low, is the lowest that they actually commit to saying. They'll never say zero, but at least they can say it's less than 1%, so where I live it's perfectly safe. Now the problem with radon, obviously it seeps out the ground, especially if you've got a basement or a cellar or something along those lines. The radon gas can seep into that area. Radon itself is an alpha emitter. When it's outside the body it's not that big a deal, but if we breathe it in it can emit alpha, and those alpha particles, if they're inside the body, can obviously cause problems, eventually may lead to cancer, lung cancer, something like that. As I said though, in the UK it's actually very low in general. We've got very little to worry about, and in the West Midlands where we are, we've got even less to worry about. Like I said, where I live the risk is less than 1%, so it's nothing that we should really be focusing on or stressing about there. Apart from radon then, there are quite a few other natural sources of background radiation. In food and drink you'll find that a lot of things that we eat will contain very low levels of radioactive isotopes, and they will emit some radiation. Exactly the same with buildings and the ground, so rocks and whatever we make bricks out of, again will contain some radioactive isotopes that will emit radiation. From cosmic rays, we're obviously getting cosmic rays coming from the sun. They collide with the gases in the upper atmosphere and will cause, again, some radiation to be cascaded down from the upper atmosphere. There are obviously some artificial sources, and you can see that the vast majority of artificial background radiation comes from medical applications. And at GCSE you would have studied some of those medical applications of radioactive substances. When we get down to the more sinister side for nuclear weapons, you can see that actually the amount of background radiation that we get from nuclear weapons is very, very small. It is a tiny percentage of what is actually being produced by the natural sources of radiation. So very, very small, tiny, almost negligible levels are coming from nuclear power. There are obviously other sources, which is really just a miscellaneous catch-all to say there are other things going on that are going to emit some radiation, but again you can see that that is very small. Now, as I said, realistically, the amount of background radiation that we are getting is small, and so small that actually there is no need for us to worry about it whatsoever. It's not going to cause us, over the course of our lifetime, any repercussions or any health effects from that. Finally today then, we're just going to have a quick look at some of the safe handling rules to do with radioactive sources. Now, on the left hand side of the screen you can see an extract from the CLEAPS hazard card. Now, for those of you that don't know, CLEAPS is an advisory service for schools to do with all things science equipment. For those of you who do chemistry and or biology, you may have seen these cards before. There's one for basically every substance that we could ever think about using in a school, especially any that you guys might handle. If you at some point just pause the video and have a read through all that, that gives you obviously quite a lot of information, probably more information than you could ever want or need at A level. But I'll try and take us through some of the more relevant points and talk you through the kind of rules and regulations and guidelines that we have to abide by as teachers, especially when we're handling these radioactive sources. Now, on the right hand side you can see a picture of a typical box that one of these radioactive sources will be found in. The source itself is this bit just here. And you can see the ruler next to it does show it is quite small. It's only really a few centimetres long, and it's shaped, if we look at it in profile, it's shaped kind of like that shape. The radioactive substance itself will sit just at the back of the cup, okay, in that area there, and you can see that on the front there's like a mesh covering. It doesn't fully cover it, it's just one of the ways of trying to keep that radioactive substance in there. But you can see they are quite small in the grand scheme of things. Like I said, only sort of 2.5 centimetres long. Now, the box itself is made of wood. It's just a standard wooden box. But what is the interesting bit is the holder in the centre is lined with lead. So the source itself would go face down into that little lead cup there. On the top there is a lead disc which would then go to cover the source. While it's been stored then, that source is completely surrounded by lead. I know it's probably only 5-6 millimeters thick, something like that, but even that will do quite a good job of stopping quite a lot of radiation. It will definitely stop the alpha radiation, it will definitely stop the beta radiation, or at least the vast majority of those. Some of the gamma will go through it, but again, a lot of the low level gamma will be stopped by that lead. That box will always be stored in a safe, okay, and the safe is locked, always under lock and key. And whenever any of us as staff want to use it, we have to sign it out in a book, so there's always that paper trace to see who's been accessing it, and obviously when we return it, it has to be signed back in. It's always checked on a regular basis, just to make sure. One of the biggest headaches we could ever have as a school is if we did accidentally lose one of these. That would be a lot of paperwork, it would be a lot of hassle and a massive headache if that were to happen. So we just need to make sure that we keep that side of the paper trail obviously absolutely correct. When we're handling it itself, you can see that in the second bullet point in the bottom section, in the control measures, it says use a handling tool. And you can just use some kind of tweezers, some kind of tongs, as you can see, at least 10 centimetres long. We normally use tongs that are near 30 centimetres long, just to make sure. And we're always going to handle the source using those tongs to keep them well away from our body. In the last bullet point of the control measures, you can see that it says here, by the use of tray sheets and absorbing paper. What we have in physics is separate trays and separate apparatus that we only use when handling radioactive sources. That's just to make sure there's no cross-contamination between the source and the equipment or anything like that. Again, just to make sure that everything is safe. Now realistically, you can see that in the first bullet point here, it does say use low activity sources. Realistically, the sources that we've got in school are extremely low. The risk that they pose is low. It's not zero, but it is low. So there is still a slight risk, but as long as they are handled correctly, there's no more risk than doing any other day-to-day activity realistically. Of course, if we were in a lab right now and I was showing you, one of the key things says that you guys as pupils should be kept at least 2 metres away. Obviously at 2 metres, very little alpha, very little beta is going to get to you. And as we saw with the inverse square law for gamma, that's going to negate a lot of the risk of the gamma that you might be exposed to as well. You can also see in the third bullet point it says that we have to have a clear set of local rules, and there is a standard document for schools that we obviously have ourselves that describes exactly what should be done, and as staff we just check up on that and reread that and just make sure that we are aware of all of the safe handling rules that we've talked about right now. Finally then, you can see that we have the trefoil symbol at the top, which is the standard ionising radiation symbol. And if we were ever in a room or ever in a lab where we were using any kind of radioactive substance, then we would have that symbol displayed prominently, normally on the door to warn anybody coming into the lab. And obviously if I was doing any kind of demonstration with a radioactive source, then I would be telling anybody in that room that's exactly what we were doing, just making sure that it wasn't going to cause any problems, and just to make sure that you are all aware of some of the rules that we need to make sure we abide by while we're handling radioactive sources. So that's it for today's lesson then. It's been a little bit information-y, which is why I've kept the lesson a little bit shorter than we have done previously. Obviously the main physics theory thing that we've looked at is the inverse square law for gamma, where the intensity of gamma radiation is inversely proportional to the distance squared. So that's the distance between the source and any kind of detector. It is an inverse square law, so we treat it exactly the same as any other inverse square law that we're going to be dealing with as part of this course. And then from the information point of view, we had a look at background radiation, what the sources of background radiation are, and some of the safe handling rules to do when we are handling radioactive sources. So that's it for this lesson. Thank you very much, and I'll see you next time.